Hello and welcome. In this lesson, we are going to talk about number bases. At the end of the lesson, you'll be able to convert a number from any base to decimal, and you should be able to perform simple calculations using modular arithmetics. Let's get started. A number base, which is also called radix, is the number of unique digits, including 0, used in a number system. So a number base is just a number system, which is just the number of digits we are using in that particular system. For example, base 10, which is called decimal, the base 10 is actually the common one we use, the common numbers we use, the base 10. It is the most commonly used number base, that's base 10. And the digits it's used, the digits used in the base 10 system are 0 to 9. That is in the base 10, which is the decimal base. The digits used are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So in base 10, there are 10 digits being used, and they are 0 to 9. If you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so those are 10 digits. And like I said, base 10 is a normal base we use. When we say numbers normally, those numbers we are saying are in base 10. For example, we say 679. 679, that is in base 10. Okay. Or you say 1520. That's also in base 10. So the numbers we use in our day-to-day conversation or in our day-to-day calculations, they are decimal numbers, that is, they are numbers base 10. And you can see that the digits we use are always 0 to 9. If I say 672 now, it means there is 6, there is 7, and there is 2. So the digits are 0 to 9. So base 10 or decimal is the most commonly used number base, and the digits it's used are 0 to 9. Some other common number bases are base 2, which is called binary. Digits used in binary is 0 and 1. Okay, so in base 2, just 0 and 1 are the digits used. Binary numbers are usually used in digital systems. Base 8, which is called octa, uses 0 to 7 as the digits. That is, in base 8, we have 0, 1, 2, 3, 4, 5, 6, and 7. And base 8 is historically used in computing. Of course, I've talked about base 10, which is the decimal, is the digits used are 0 to 9, and base 10 or the decimal is the standard system, the normal system we use. Base 16, called hexadecimal, uses digits 0 to 9 and letters A to F. So base 16, which is the hexadecimal, is also used in computing. So base 16, we have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have A, B, C, D, E, F. Okay, so I want you to notice that in a particular radix, in a particular number base, the number of digits that are being used there is the same thing as the base. For example, in the binary system, which is in base 2, the digits that are used are 0 and 1. So in base 2, the number of digits being used is just 2, 0 and 1. Okay, in base 8, digits being used is 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7. So that is 8 digits that are being used in base 8. And in the base 10, which is the decimal system, the digits being used are 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in base 10, 10 digits are being used. Also in the hexadecimal, which is the base 16, the number of digits being used, we have 10 digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 10 digits. Then we now have 6 alphabets to add to that. A, B, C, D, E, F. So in the base 16 or hexadecimal, there are also 16 items being used. Then I want to mention that in that hexadecimal, the A actually represents 10. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that A is like representing 10. The B is like representing 11. C is representing 12. D is representing 13. E is representing 14. And F is representing 15. Then one final thing I want us to also note is that in the number base system, the digits are never up to the base. This in base 2, the digits used are 0 and 1. You cannot have 2 in base 2. You cannot have 3 in base 2. No, the digits are 0 and 1, less than that base. And in the base 8, which is the octal system, digits used are 0 to 7. They are less than that base 8. You cannot have 18, 1 and 8 in base 8. No, because even though 1 is less than 8, 8 is up to 8. And you cannot have 92. base 8 because 9 is already greater than 8. Base 10 is the decimal number. You cannot even have any number more than base 10 because the digits are 0 to 9. If you have 11, but it's just 1 and 1, so that's quite okay. And base 16 is also fine because you have 0 to 9 and A to F. Remember, you don't have any alphabet after F in base 16. It's just 0 to 9 and A to F. We now discuss the concept of positional notation in number base. Positional notation is a concept that describes that the value of a digit depends on its position and it represents power of the base. That is, in number base, the value of each digit in a number base, the value of each digit, the value of that digit depends on its position and it represents the power of the base. For example, if we say in base 10, we have 678. The value of that 6 depends on the position of that 6. The value of that 7 depends on the position of that 7. And the value of that 8 depends on the position of that 8. 678. The 6, 7, and 8, they are not the same thing. Because 6 is 600. 7 is 70 or 7 tenths. While 8 is just 8 units. So in number base, the value of a number depends on its position. And that position is representing the power of the base. So in 678, the 6 is 100. That is, it is 6 times 100. You can say that is 6 times 10 to the power of 2. But we are in base 10. We said it is representing power of that base. So that 600 is 6 times 10 to the power of 2. Then the 7 is 7 tenths or 70, right? It is 7 times 10 to the power of 1. And the 8 is 8 units. That is 8 times 10 to the power of 0. So 678 is 6 times 10 to the power of 2 plus 7 times 10 to the power of 1 plus 8 times 10 to the power of 0, right? And then in base 2, if you have 11101, again, the value of each of these digits depends on their position. So this first one here is like 1 times 2 to the power of 4. Now, to be able to get the powers, you can start from the right end here and put powers from 0 upward so you get to the left end. So if you start from the right end here, you see this is power 0, then this 0 is power 1, then the next one is power 2, the following one is power 3, and the last one here is power 4. So when you do that, it means that you can realize that this first one on the left here is power 4. So that is 1 times 2 to the power 4 plus 1 times 2 to the power 3, that is the second one, plus 1 times 2 to the power 2, that is the third one, then plus 0 times 2 to the power 1, this is this 0 here, then plus 1 times 2 to the power 0. So to get the powers, you start the numbering of the power from the left end, then you go to the right end. That is from this left end 0, then you go 1, 2, 3, and 4. So that is 1 times 2 to the power 4 here is 16, plus 1 times 2 to the power 3. 2 to the power of 3 is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So 1 times 8 is 8. I think it's important to repeat that. 2 to the power 3 means 2 times 2 times 2. It is not 2 times 3. 2 to the power 3 is 2 times 2 times 2. Then 1 times 2 to the power 2. 2 to the power 2 is 2 times 2, which is 4. So 1 times 4 is 4. 0 times 2 to the power 1, you mean that 0 times anything is 0. Then plus 1 times 2 to the power 0. Any number to the power of 0 is 1. Of course, apart from 0 itself. So 2 to the power 0 is 1. And 1 times 1 is 1. Then finally, you can add 16 plus 8 plus 4, 0 plus 1. And that gives us 29 in base 10. So 11101 in base 2 is the same thing as 29 in base 10. I'm still going to talk more on converting numbers to binary, to the decimal system. So now we'll now talk about converting between bases. We start with converting from a decimal number to a binary number. We know that a decimal number is a number in base 10, while a binary number is a number in base 2. So if you want to convert a number from a decimal number, that is base 10, to a binary number, what we do is that we are going to divide that number by 2. And when we are dividing the number by 2, we will be tracking the remainders. Please note that. We will be tracking the remainders. So we are converting a decimal number, which is a number in base 10, to a binary number, that is to a number in base 2. we divide by 2 and we'll be tracking the remainders. So let's do that. Let's convert 13 in base 10 to binary. That is, we want to convert 13 in base 10 to base 2. So we divide 13 by 2. That is going to give us 6, right? 13 divided by 2 is 6, and a remainder of 1. You can see that we are tracking the remainder, right? Remainder 1. Then we'll continue again. We divide 6 by 2, get 3, and a remainder of 0. Okay. Then we do 3 divided by 2, get 1, and a remainder of 1. We do 1 divided by 2, because 1 divided by 2, 1 cannot be divided by 2 because 1 is less than 2. So 1 divided by 2 is going to be 0. Then the remainder will be the 1 itself. Once you get to a number that cannot be divided by the base, you said that division is 0, and the remainder will be that number itself. So the remainders we have here is 1, 0, 1, 1. But we are going to now take that remainder from the last one upward. That is, from this one that is the last one here, take it upward. So we have 1, 1, 0, 1. That means that 13 in base 10 is 1, 1, 0, 1 in base 2. So that is how to convert a number from decimal to binary. That is, to convert a number from decimal, which is base 10, base 2, we are going to divide the number by 2 and we track the remainders. And finally, we take the remainders from the last one upward. What of conversion from binary to decimal? That is, we want to convert a number from base 2 to base 10. Remember, we've said that the value of a number in number base depends on its position, right? So we are going to use that idea here. To convert a number from binary to decimal, we are going to multiply by powers of 2, because the number is in binary, it's in base 2, right? So we are going to multiply the number by powers of 2, then we sum the results. For example, remember that we multiply the number by powers of 2 because we are coming from base binary, which is base 2, sum the result. For example, if you want to convert 1101 base 2 decimal, that is, we want to convert the result we got back to decimal. Now, positionally, 1101, remember I said you take the power from the left end to the right end. So 1101 comes from the last one here, which is the left end. You see that is power 0. The following 0, which is the next digit, will be power 1. Following digit, which is 1, will be power 2. The last digit, which is 1, will be power 3. So hence, that will be, and that is powers, and those powers are actually powers of the base. Remember that we said that when we talked about positional notation, that these powers, they are powers of the base. This is not actually, it doesn't mean 1 to power 3. It's actually, this 3 is for the base. It is 1 times 2 to power 3. So after this positional arrangement, it means that we have 1 times 2 to power 3, and plus 1 times 2 to power 2, that is for this second digit, plus 0 times 2 to power 1, that is for the third digit, then plus 1 times 2 to power 0, that is for the final digit here. So like I said, 2 to power 3, please note, 2 to power 3 is not 2 times 3. 2 power 3 means 2 times 2 times 2. 2 to power 3 means multiply 2 by itself 3 times. So 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So 1 times 2 to power 3 is 8. Then plus 1 times 2 to power 2. 2 to power 2 is 2 times 2, which is 4. 1 times 4 is 4. Then plus 0 times 2 to power 1. Since I have 0 here, anything multiplied by 0 is just 0. Then plus 1 times 2 to power 0. 2 to power 0 is 1. Like I said earlier, any number to power 0 is 1. So 2 to power 0 is 1. Then 1 times 1 is 1. Finally, if I add 8 plus 4, that's 12. Plus 0, still 12. Plus 1, that is 13. So that means that 1101 in base 2 is 13 in base 10. Now, how do we convert a decimal number, that is a number in base 10, to hexadecimal? This is going to convert from base 10 to base 16. Similarly to converting from decimal to base 2 to binary, you know, when we converted from decimal to binary, what we did was we divided by base 2, because 2 is the base for binary, divided by 2, and we track the remainders. So if we want to convert from decimal, which is base 10, to hexadecimal, which is base 16, we divide by 16, we are going to track the remainders. I think I should just state at this point that if you are converting from decimal, that is from base 10, to any other base, what you do is you divide by that base, that other base. This is converting from base 10 to any other base. You divide by that other base and you track the remainders. So when we did decimal to binary, Binary is base 2. So from base 10 to base 2, divide by 2, and we track the remainders. Now that we want to do from decimal, which is base 10, to base 16, we are going to divide by 16 and we're going to track the remainders. So example is, we want to convert 225 to hexadecimal. Note that the 225 here didn't indicate any base. That's because naturally decimal is the natural base. So when we don't indicate any base, and we assume that the base is 10. So if you want to convert 225 to hexadecimal, like I said, because you are converting from base 10 to any other base, which is base 16 in this case, you divide by that other base, which is base 16, and you track the remainders. So when we divide 225 by 16, 225 divided by 16 is 15, and it gives us a remainder of 15, or F. Remember that when we mentioned hexadecimal, we said the digits are 0 to 9 and A to F. And we said that A represents 10, B represents 11, C represents 12, all the way to F representing 15. So when you do 225 divided by 16, and you get 15 remainder 15, that remainder of 15 can be represented as F. Please notice the remainder of 15 that is represented as F, not the quotient of the division. Then this 15 that we have here, we have to divide it by 16 again. That will be 0, remainder 15, right? Because you cannot divide 15 by 16 because it's less than it. So 15 divided by 16 will be 0, remainder 15. Okay, and again, you can represent the remainder of 15 with F. Then we take the remainders from the last one upward. That is from this one that is last, this F that is last, then upward. That will be FF. Anyway, it's just F. So 255 base 10 is the same thing as FF in base 16. Let's remember that F is representing 15. So 255 in base 10 is FF base 16. We can also convert from hexadecimal to decimal. That is, we can convert from base 16 to base 10. Again, to convert from hexadecimal to base 10, we are going to multiply by powers of 16 and sum the result. Just we can compare this to when we converted from binary to base decimal, whereby we multiplied by powers of 2 and sum the results. And then we can again now generalize that if you are converting from any base decimal, we're going to multiply by powers of that base and sum the results. Let's state that again. If you are converting from any base to base 10, you're going to multiply by powers of that base, then sum the results. And if you are converting from base 10, any base, you're going to divide by that base and track the remainder. Those two statements are very, very important. So let's convert FF to decimal. So FF is 15 and 15. Remember that, because in hexadecimal, F represents 15. So convert FF to decimal. So if you use the positional arrangement, go from the right end. This F, that is the last F on the right end, is positionally 0. Then this second F, which is the first F, the second digit, the second F from the right end, be positionally 1. So FF, and like I said, that those powers are actually for the base, not for the digits themselves. So FF base 16 will be 15, which is the F itself, times 16 to power 1, that is the positional arrangement with the positional value for this F, then plus 15, which is the first F from the right end, times 16 to power 0. Power 0 is the positional value for the first F from the right end. So this is 15 times 16, that is 240, plus 16 to power 0 is 1. Remember I said any number to power 0 is 1. Then 15 times 1 is 15. So 240 plus 15 is equals to 255. So FF base 16 is the same thing as 255 base 10. It's because the result we started with initially. That brings us to the end of the lesson on number bases. In the next lesson, we'll talk about modular arithmetics, its applications, and solve some questions involving modular arithmetic. Thank you very much for listening.